In this video, we will be learning how to add and subtract fractions when they don't have the same denominator. Well, we must remember that only fractions that have the same denominator can be added or subtracted. Let's do a little bit of a review about what a denominator is before we get into this subject. Remember, the denominator tells the size of the fraction. It also tells us the fraction's name. And of course, it tells us how many pieces make up the whole. We have a couple of examples here. Here's a circle broken into two pieces, and the denominator is a 2, telling us that 2 halves make up the whole. Here we have a square broken up into 4 pieces, so the denominator naturally is fourths. And of course, the other top part of the fraction, is the numerator. And the numerator found at the top tells us something very important. Once the denominator has established how many parts there are going to be in the whole, in this case of the fraction 3/4, it's telling us the whole circle has 4 pieces to it of equal size. But the numerator is telling us that something special is happening with 3 of the 4 pieces, and in this case they're colored green. When you don't have the same denominator, you have a special problem, and here's some examples to show you how that problem works out. If you tried to add 4 feet and 5 yards, the problem would be that you could definitely add the numbers. That would be 9. But what we would call that is the problem, because feet and yards are different size. So the way we could solve that problem would be to change the larger unit, yards, into feet. If you know your conversions here, 1 yard equals 3 feet. So 3 times 5 is 15. Now we're on an equal footing. We have the same size units being added, and when we add them up we get 19 feet. Of course, it can be converted later on back into yards. Here's a classic situation. Trying to add 7 apples and 3 oranges. Well, it's easy enough to add 7 plus 3 is 10, but what would you call it? You couldn't say it was 10 apples, and you couldn't say it was 10 oranges. So you'd have to find the common ground. And the common ground would be a common word that both of these would fall into the category of. And of course, in this case, it would be fruit. So 10 pieces of fruit would be a good answer for this problem. Okay, here's a subtraction problem. Subtracting something that is a different unit size from something smaller. Well, we can do this. We could do it in our head probably. But even if we did it in our head, we would have to convert the hour into minutes. We would have to know that 1 hour equals 60 minutes, and then it's just a matter of subtracting 60 from the 96 and getting a total of 36 minutes when we're done. So we see that fractions can have different sizes, and it's difficult to be adding them. In fact, impossible unless you change them. For instance, if we were adding these 2 fractions, here we have 1/3 written like this, and this is a circle broken up into 8 pieces, and 3 of them are colored in, so that would be 3/8. To add them, the answer would be meaningless, which means that it wouldn't make sense. So we need to do something to the fractions before we can add and subtract them. So let's take a look at that. Now remember that you only add with the top number. The bottom number is just going to tell you the size of the pieces and the name of the fraction. So we have to have that the same, and then we'll go ahead and add the numerators or subtract the numerators of the fractions involved. Well, it's really easy when the denominators are the same. Here's a simple problem. If we took 3/8 and added 2/8 to it, we don't have a problem with this. That's going to stay the same. It's going to name the fractional parts or eighths, and we're going to add the 3 and the 2, and we're going to come up with the answer of 5/8. If they were all that simple, yeah, there wouldn't be a problem. But unfortunately they're not, because so often we end up with fractions that we want to add or subtract that don't have the same size denominator. If we tried to add these two fractions together for a total answer, well, we could add the numerators all right, but the answer, if we called it fourths, wouldn't make any sense, because that wouldn't take into consideration that fifths are included. And if we turn that around and try to do the same thing by adding the numerators and getting 4 again, but then trying to call it fifths, again the answer is meaningless. So we need to try to find something common to the both of them. So this is what we do. And if you remember about equivalent fractions in a previous video, and if you don't, we'll do a little bit of reviewing, that equivalent fractions are fractions that are equal to another fraction. In this case, the simplest form, 2/5, can have an infinity of equal fractions that just get larger in numbers, but stay equal to what they started out as. Let's take an example. 2/5 can change to 4/10, 6/15, 8/20. Remember how that went? Well, we went with multiples of the denominator, 5, 10, 15, and 20, and then matched it with multiples of the numerator, second multiple of 2, onto the third one, onto the fourth one. And as long as we stayed consistent and didn't skip around, these fractions stayed equivalent. What happened was the denominator got smaller. Remember, that's the way it works with fractions. As this number gets larger, the pieces get smaller, and we made up for it by having more of them. Okay, so I've made a list of fractions that are equivalent or equal to 2/5. What I'm trying to do is to do the same thing with this bottom fraction and see how long it takes to finally get a denominator that will match. Well, I'd have to take this out a number of steps, but finally it happened right here. I finally matched the denominators at 20ths. 2/5 equals 8/20, 1/4 equals 5/20. So now we have the common ground that allows us to add without any trouble. We add the numerators, 8 plus 5, 13, and we're going to call it 20ths. This is a visual demonstration of that same problem, just using these bars. There's the 2/5, and there's the 1/4. You can see the difficulty in trying to add these because they are different sizes. When we finally settled upon 20ths as the first fractional pieces that would equally fill in a fifth and then also fill in fourths, this is what we ended up with. Okay, those 4/20, for 1/5 and the other one, and then the fourths that contained 5/20. So you add them all up and you end up with the same answer. How about this problem? Do you think you understand it well enough if we just quickly review the steps? Remember, you want to add them, or excuse me, in this case, subtract them, so that you are subtracting fractions that have the same denominator. The only way to do that is to write a list of equivalent fractions for both the top and the bottom number, and then stop when you get to a common denominator. Well, if you want to try it, pause the video and then come back and watch the demonstration of how it's accomplished. Okay, well, if you did the problem, hopefully you wrote it with the 5/6, which in this case is the larger fraction at the top. It also came first in the equation, if you remember. And so we're subtracting this fraction from it. Okay, if you made a list of equivalent fractions, you didn't really have to go very far. Okay, 3/4 changes to 6/8, but we don't get a match. But we do get a match as soon as we change this one to the next equivalent fraction and the third one in this series. Here we match the 12ths. So now all we have to do is subtract the numerators and name it as 12ths. Answer would be 1/12. How about this one? Well, give it a try and come back, or stay here and watch the demonstration. Okay, again, we're looking for a common denominator because 12ths and 8ths are not the same size. If we make the second equivalent fraction 14/16, we have to keep going because we still do not have a common denominator. Okay, when we make the second equivalent fraction for 12ths, 10/24, still no match. So we're going on, and bingo, there we are. The 24ths match. This has become that. We haven't lost anything, we've just changed it. This has become that. Same deal. We haven't lost anything, we've just changed the fractional pieces. And we're subtracting, so 21 subtract 10 equals 11. And of course we know the name of it. It's 24ths. Okay, how about this one? All right, again, we're looking for a common denominator because a 6th is larger than a 9th. You might actually know it if you can count ahead down the multiple lists of 6 and 9. You might actually already have it. But if not, then you write them out. 2/12 doesn't quite match. You might not recognize this one right away. Once you go to the second multiple of 9, which is 18, and you change this number to 10/18, you know, probably recall that 6 also is in that same category. When you're doing the multiples of 6, 18 is the third one. So you change the top number also along with it, add them up, and there's your answer. Well, that's the explanation. You certainly have to do some practicing because practicing does boost confidence. But of course, once you know how to do it, the practice will make it even better.